Suppose R is a fixed constant and a sub 0, a sub 1, a sub 2, and so on is a sequence that satisfies the recurrence relation a sub k equals R times a sub k minus 1 for each integer k greater than or equal to 1 and a sub 0 equals a. Use mathematical induction to prove that a sub n equals a times R to the n for every integer n greater than or equal to 0. So this part right here is going to be our P of n. And we'll start with our base case where we prove that P of n is true for the smallest possible integer n, which in this case would be 0. Now, first, we'll start by restating what P sub 0 is to show what we need to prove, which would be that a sub 0 equals a times r to the 0th power. I'll put a question mark, though, here just to emphasize that we're not trying to assert this. We're trying to prove this. So by asking the question, we can now check to see if this is true. Now, a times r to the 0 is just a, since anything to the 0th power is 1, with exception to 0, although I think the author meant to include in the directions that r cannot equal 0. But putting that aside, we're assuming that r cannot equal 0, so that r to the 0th power is just 1, so a times r to the 0th power is just a. But a, by assumption, is a sub 0. And so this is the proof. A times r to the 0 equals a sub 0. Now let's move on to the inductive step. Let k be an arbitrary fixed integer with k greater than or equal to 0, and assume that P of k is true. That means that our inductive hypothesis is the statement that a sub k equals a times r to the k. What we want to show, WWTS, is what we want to show is that P of k plus 1 is true, which is the statement that a sub k plus 1 equals a times r to the k plus 1. Now, the way we're going to show this is we're going to take the left-hand side here and do stuff to this. Now, according to the recursive definition of the sequence, for every integer k greater than or equal to 1, well, k plus 1 is greater than or equal to 1 since k is greater than or equal to 0. We can add 1 to both sides of this inequality here to get k plus 1 is greater than or equal to 1. And that's super important because we need to know that this index value is at least 1 so that we can apply this recursive definition. So now we know we can apply this recursive definition, meaning that each term is equal to r times the previous term, meaning that a sub k plus 1 is r times the previous term, a sub k. So that's by the recursive definition of the sequence. But now we can apply the inductive hypothesis, because the inductive hypothesis tells us what a sub k equals. So we're going to replace a sub k with a times r to the k. And remember, in the inductive step, whenever you apply the inductive hypothesis, which you have to apply the inductive hypothesis at least once, then you have to clarify to the reader that you're using the inductive hypothesis. So this equal symbol here is only true because of the inductive hypothesis. But now we can rewrite this as a times r to the k. And we can use the law of exponents to add these exponents together and group together these factors of r so that this is a times r to the k plus 1th power. And that's what we wanted to show, is that a sub k plus 1 equals a times r to the k plus 1. That proves that P of k plus 1 is true, which means that by mathematical induction, P of n is true for all integers n greater than or equal to 0. Thanks, everyone, and I'll see you in the next video.